Okay, let's dive right into this explainer. We're going to explore how ancient, catastrophic stellar explosions completely rewrote the night sky and, literally, forged the very building blocks of life itself. You know, we often look up at the stars and think of the universe as static, just this unchanging backdrop, right? But the reality is that our cosmos is incredibly dynamic. Throughout human history, the sky has occasionally just erupted with sudden, brilliant light. So today, we're going to decode those ancient flashes and see exactly how they gave birth to modern astrophysics. Here's our roadmap for today's time detective journey. We'll start with ancient eyes on stellar death, then move to SN 185, the first guest. After that, SN 1006, the brightest star, followed by SN 1054, the Crab Nebula. And finally, we'll wrap up with our cosmic origin. So, Part 1. Ancient Eyes on Stellar Death. To truly understand our cosmic origins, we have to look through the eyes of the very first stellar detectives. Long before we had space telescopes, early observers meticulously documented the arrival of what they called guest stars. Now, it actually took humanity thousands of years to realize that these guests weren't polite little visitors at all. They were the violent, explosive deaths of massive stars. Honestly, think of them as the ultimate bad house guests, arriving totally unannounced, making a massive scene, and then refusing to leave for months. Let's map out our journey across nearly a millennium, focusing on 3 specific dates: 185, 1006, and 1054 CE. These aren't just random years in a history book. For astrophysicists, these exact dates serve as absolutely vital historical anchor points. By combining ancient records from these years with modern telescope data, scientists have been able to reverse engineer the life cycles of stars. It's pretty amazing. Which brings us to Part 2. SN 185, the first guest. Our investigation kicks off in the year 1805 CE. Chinese astronomers spotted a sudden glowing beacon situated between the constellations of Circinus and Centaurus, about 8,000 light-years away. Imagine tracking the familiar patterns of the night sky, only to suddenly find this blazing light that just wasn't there the night before. The crucial point here is that this explosion was so unimaginably massive, it hung visible in the ancient sky for a staggering 8 months. For over 2/3 of a year, anyone looking up would have seen this ghostly visitor. Fast forward almost 2,000 years, and our modern telescopes have finally located the shrapnel from that flash of light. We're looking at a distinctive, expanding ring of debris that scientists today call RCW86. Finding this remnant was kind of like finding the smoking gun at a cosmic crime scene. It's what allowed us to finally transition from historical guesswork to hard, physical evidence. By analyzing this specific remnant, scientists proved SN 185 was what we call a Type 1a supernova. This happens when a dense white dwarf star acts like a cosmic vampire, basically siphoning material from a companion binary star until it hits critical mass and just detonates. X-ray analysis of this debris revealed extensive iron deposits. But you know what the true breakthrough was? They found that high-velocity stellar winds had actually created a preformed cavity around the star right before it exploded. This perfectly explains why the debris expanded with such blinding speed. It's wild how this one ancient observation fundamentally refined modern astrophysics. Moving on to Part 3, SN 1006, the brightest star. Let's jump forward nearly 8 centuries to April 30, 1006 CE. In the constellation Lupus, we get the absolute peak of stellar events in recorded human history. I mean, if you thought the 8-month guest star was impressive, wait until you hear about the sheer power of this one. SN 1006 reached an estimated visual magnitude of -7.5. To put that into perspective, it was approximately 16 times brighter than Venus at its maximum brilliance. It was so extraordinarily luminous, you could clearly see it during broad daylight. Imagine just looking up at noon and seeing a secondary blazing point of light trying to compete with the sun. Unbelievable. This event was so undeniable, it was witnessed globally, documented across China, Japan, Iraq, Europe, and possibly even in North American petroglyphs. Just listen to this awe-inspiring account from the 11th century Egyptian astronomer Ali ibn Ridwan. He described it as a large circular body 2.5 to 3 times as large as Venus. The sky was shining because of its light. That incredible qualitative data from 1,000 years ago is exactly what helps modern scientists beautifully calibrate their own historical models today. Modern calculations place this blast roughly 7,200 light-years away, firmly within our own Milky Way galaxy. But even at that incredible distance, those 1,000-year-old human observations remain absolutely critical. Scientists use multi-wavelength observations to study the remnants' complex physics today, sure, but they actually rely on those ancient diaries to establish the exact timeline of the explosion's evolution. It's this perfect handshake between ancient history and modern science. All right, Part 4, SN 1054, the Crab Nebula. Just a few decades later, on July 4th, 1054 CE, astronomers documented another new star, this time in the constellation Taurus. This specific case perfectly shows the evolution of human astronomy across 3 distinct eras. Step 1. Ancient eyes witnessed the initial blast in 1054, which temporarily outshone everything else in the night sky. Step 2. In 1758, Charles Messier catalogs a strange, cloudy structure in space, naming it M1. And Step 3. In the 20th century, astrophysicists finally connect the dots, realizing Messier's cloud was the direct aftermath of that 1054 explosion. Today, we know that expanding cloud as the famous Crab Nebula, located near the star Zeta Tauri. But what researchers found right at the heart of this nebula is truly mind-blowing. They discovered the Crab Pulsar. This is an extraordinarily dense, rapidly rotating neutron star that emits regular pulses of radiation. It is literally the crushed, beating heart, the stellar core, that somehow survived the catastrophic destruction of its parent star. SN54 basically gives us a completely documented narrative of stellar evolution, destruction, and rebirth. And finally, Part 5, our cosmic origins. As we pull all these clues together, from ancient handwritten records to modern X-ray imagery, what you should really take away from this explainer is that these cataclysmic explosions aren't just spectacular cosmic light shows. They are the ultimate foundries of creation. In their dying moments, massive stars forge and violently scatter heavy elements across the galaxy. The iron in your blood, the calcium in your bones, they were literally forged in the heart of stellar catastrophes exactly like the ones witnessed in 185, 1006, and 1054. Knowing that ancient civilizations left us this meticulous map to the most violent and beautiful remnants in the galaxy, we are truly left standing on the shoulders of giants. We now have telescopes that can peer to the very edge of the observable universe. But all of this forces us to ask an exhilarating question. What will our modern instruments and our modern eyes see when the next great guest star finally arrives in our own cosmic neighborhood?